One of the most important systems in your car are the brakes. In fact, they are so important that they are one of the few systems that are specifically covered by governmental regulations. And this is true not just here in the US, but all over the world. Hello, I'm Huibert Mees, and this is Suspensions Explained. Here in the US, brakes are covered by the Federal Motor Vehicle Safety Standard number 135, also known as the FMVSS 135, and similarly in Canada, they are covered by the CMVSS 135, while in the rest of the world they are covered by some variant of the ECE R13H. What all these regulations do is dictate the minimum performance requirements of your brakes. Things like what happens in the event there's a failure in your brake system, what the warning light on the dashboard needs to look like, and what sort of things would trigger the light to come on, how easy it is to see the fluid level in your brake reservoir, how steep a hill the parking brake must be able to hold the car on, and how well the emergency brake needs to be able to stop the car in case you have a brake failure. The average customer has also become accustomed to a minimum level of performance in your brakes. Things like brake pads that are quiet, brakes that don't require a bodybuilder's leg to stop the car, and brake pads and rotors that last a long time. So how does a brake engineer go about designing a brake system that meets all these customer requirements, but also meets all the regulation requirements? Let's see what goes into the design of a brake system, and then we'll worry about whether or not we meet the regulations. Basically, the brake system is made up of the brake pedal, which is connected to the booster, some sort of anti-lock system, an ABS system, the calipers and rotors for the front, the calipers and rotors for the rear, and the brake lines that connect them. For the moment, we're going to ignore the anti-lock system because as long as the tires aren't slipping, the system is not active anyway, so this will be the system that we'll be talking about here. The sizes of the components in the brake system will dictate how well the brakes work and how well they will stop your car. Here are the dimensions of each of these components that affect the performance of your brakes. We need to know the tire SLR. SLR stands for static loaded radius, and this is the distance from the center of the wheel to the contact patch on the tire in its deflected position. So you need to have the car sitting on its tires with the weight of the car on the tires, and that will deflect the bottom of the tires slightly. And this is the distance from the contact patch then to the center of the wheel. We need to know the effective radius of both the front and the rear rotors. The effective radius is not the radius of the rotor itself. It is the average working radius of the pads as they are pressed against the rotors. And it is something that the caliper manufacturer provides as part of the data that they provide for any caliper. Next, we need to know the piston diameter of the calipers. And there may be more than one piston in a caliper. In the case of the model here, we only have a single piston caliper, so we only have a value in for one of the diameters. We need to know the friction coefficient of the pads. This could be different in the front or the rear. This is the friction coefficient between the pads and the rotors. Normally, these values are somewhere in the 0.3 to 0.45 range. They don't wander much outside of that, because if it's lower, then the brakes aren't very effective. And if it's higher, the pads tend to chew up the rotors very quickly and you don't have as good of rotor life. So normally you will see values here between 0.3 and about 0.45 at the max. We need to know what the master cylinder diameter is. Also, we need to know what the boost ratio of the booster is. This is the multiplication factor of the input force of the booster to the output force. So it's how strong is the booster. And we need to know what the brake pedal motion ratio is. The brake pedal itself, by its design, amplifies the force from your foot as you push on the brake pad, and it's that ratio of force that we need to know here. Normally, these are in the 3 to 4 range. These parameters are by no means the only things that the brake engineers need to know. For instance, they say nothing about the stopping power of the brakes, which will require knowing about the thermal mass of the rotors, the pad area, the amount of airflow flowing around the brakes and the wheels. But they tell us how strong the brakes will be, how much force they can generate to stop the car. To better understand this, let's see what happens when we push on the brake pedal. You press on the brake pedal with your foot, and let's suppose you do this with a force of 50 newtons. Because of the motion ratio of the brake pedal, this force is multiplied before it goes into the booster. Let's assume a brake pedal motion ratio of 3. This means the force going into the booster is 3 times 50 equals 150 newtons. The booster itself has a boost ratio that again multiplies this force and then pushes on the master cylinder. Let's say the boost ratio of our booster is 6. This means the force going into the master cylinder is 6 times 150, which equals 900 newtons. Inside the master cylinder is a piston that pushes on the hydraulic fluid. This piston has a certain diameter and area which translates the force coming from the booster into hydraulic fluid pressure. Let's say our master cylinder has a diameter of 25 millimeters. This means the area of the master cylinder is 25 squared times pi over 4, which equals 491 square millimeters. Our 900 Newton force will now translate into 900 divided by 491 equals 1.83 newtons per square millimeter. This hydraulic pressure travels down the brake lines to each of the 4 calipers where it pushes on the pistons. The area of each piston determines how much force the hydraulic pressure creates. For our example, let's assume we have a front piston diameter of 65 millimeters, which gives a piston area of 3,318.3 square millimeters. And let's assume we have a rear piston diameter of 42 millimeters, which gives an area of 1,385.4 square millimeters. These are fairly typical values, by the way. If we have 1.83 newtons per square millimeter of pressure, then the front caliper will generate a force of 6,072.5 newtons, and the rear calipers will generate 2,535.3 newtons of force. Notice this is not braking force I'm talking about here. This is the clamping force. This is how hard the pistons are pushing the pads against the rotors. In order to calculate how much stopping force all this will create, we need to remember that there are 2 pads in each caliper, and there are 2 calipers on each axle. Each of these pads sees this same clamping force. So the total clamping force on the front axle will be 4 times this 6,072.5 or 24,290 newtons, and the total rear clamping force will be 10,141.2 newtons. Now these forces are acting on the brake pads and trying to push them against the rotors. So in order to calculate the actual braking force that we are generating, we need to take into consideration the friction coefficient between the pads and the rotors. In this case, we have assumed our friction coefficient of 0.35, which means that for the front braking force, we have a total braking force being generated of 8,501.5 newtons. And in the rear, the braking force will be 3,549.4 newtons. To calculate how much stopping force this actually creates, which is the force created at the tire contact patch, we need to take the effective radius of the rotor and the tire SLR into account and multiply this force by the ratio of those 2 numbers. In the front then, what we get at the tire contact patch is a stopping force of about 3,750 newtons, and in the rear we have a stopping force of 1,305 newtons. What this means then is that the total braking force at the tires in the vehicle is 5,055 newtons. If we have a vehicle that weighs 2,000 kilograms, that means that we will have a deceleration rate of 2.53 meters per second squared, or 0.26 G. That's not a lot, but then 50 newtons of pedal pressure isn't very much either. We can run these calculations for a range of different pedal forces and graph the results. In the case of our example, this is the graph that we would get. Notice that our curve is a straight line. This is typical of a basic brake system because the harder you press on the brake pedal, the more hydraulic pressure you will create, and the relationship between pedal force and hydraulic pressure is linear. In other words, if I double the pedal force, I will double the hydraulic pressure, and therefore I will double the braking force the calipers create. You can see here where the example we just ran through would fall on this graph. But how do we know that this is enough? How do we know that the effective radius of the rotor that we are using, the piston diameters, the boost ratio, etc., is correct for our car? To answer that question, we need to look at the ideal brake curve for our car and overlay that with the graph we just created. If you're not familiar with the ideal brake curve, you can watch my video here and learn all about it. If you haven't seen it, take a break and watch it because it is pretty critical to understanding the rest of this discussion. Here we see the ideal brake curve for our car and the actual brake graph overlaid. What we are looking for is to make sure the actual graph is below the ideal curve most of the time. The reason for this is when the actual graph is below the ideal curve, the front wheels will lock up before the rear wheels do. This ensures stability of the car during a wheel lockup event. You can see what happens when the rear wheels lock up first in this video here. We also want to see at what point the actual graph crosses over the ideal curve. This is called the Z-critical point. In the days before anti-lock brakes, it was important to make sure the actual graph was always below the ideal curve, but nowadays we can let the curves cross each other and rely on the ABS system to prevent lockup of the wheels and maintain vehicle stability. Still though, we don't want to rely on the ABS system too much. So we still want to make sure our brake system is inherently stable, which means we want this crossover point to happen at very high G levels, ideally above 0.8 Gs. You can see that's not the case here. Our crossover point is barely above 0.7 Gs. This means the balance between our front and rear brakes is not right yet, and we are getting too much braking out of the rears. Let's see what happens if we put smaller rotors on the front. This is reflected in the effective radius of the rotor, and so we'll change that from 150 down to 125 to match the rears. Oops, that went the wrong way, but it makes sense. Making the front effective radius smaller means the front brakes aren't as strong. Let's put that one back and instead change the rear caliper piston diameter from 42 to 40 millimeters and see what happens. That's better. This change did exactly what we needed, and now our Z-critical is above 0.8 Gs. We could also have changed the friction coefficient of the front pads, but you do have to be careful here, because if you start going too high, you'd run into other issues like brake squeal and premature wear of your rotors. Increasing the master cylinder diameter, playing with the pedal ratio or the boost ratio would have changed our curve as well, but it wouldn't have changed the balance between the front and the rear because the same pressure is being sent to both the front and the rear brakes. So any changes we make to the booster end of things would have affected the front and the rear the same amount. Now what we want to look at is the difference between the curves. The idea of any brake system is to get as close as possible to the ideal brake curve. This means we would be using the front and rear brakes to their maximum potential under any road conditions. In this case, though, there is a big difference between our curves, especially in the middle region. This area represents what would happen on a more slippery road surface, like when it rains. Wet pavement can have a friction coefficient between about 0.5 and 0.6. So if we look at the 0.5 line in our graph, remember, these diagonal lines represent the friction coefficients of different road surfaces and conditions. We can see that this line crosses our actual curve way below the ideal curve. What this means is that on wet pavement, we can expect the front brakes to lock up fairly early, at which point the rear brakes are not nearly at their limit yet. We would be losing a lot of total braking capability with this system under those conditions. Of course, we could always let the ABS system take care of things for us and keep the front wheels from locking up until the rear wheels are at their limit too, and that's what a lot of cars do nowadays. But I've always been of the opinion that we should design the basic system as best as possible and not rely on the electronics to save the day. The electronics could fail one day, but we'd still want the car to be able to stop properly. Also, if you're trying to size brakes for a race car, you may not have an ABS system at all. One way to deal with this would be to adjust our brake system parameters to bring our actual curve closer to the ideal curve. Something like this. Here, all I've done is increase the rear caliper piston size to 45 millimeters. But now our Z-critical is much lower, and that's not good either, because even though we've improved the situation in the wet pavement area, i.e. at the 0.5 line, we've made the situation on dry pavement much worse. And on dry pavement, we would now expect to get rear wheel lockup much earlier than front wheel lockup, and that's not good. The answer is something called a brake proportioning valve. It was very common in the days before ABS, and it works like this. The valves are placed in the hydraulic lines going to the rear brakes. Under low brake pressures, the valve just lets the fluid pass through. In other words, the same pressure going to the front also goes to the rears. Once the brake pressure reaches a predetermined level, a valve closes and only a portion of the pressure is allowed to get through. Both the activation pressure and the proportion ratio are tunable and determined as part of the design of the valve. Let's see what happens if we add a proportioning valve to our design that activates at 3.5 newtons per square millimeter pressure and has a proportion ratio of 0.5. Notice how there's now a kink in the curve. This is the point where the proportioning valve kicks in, and from there on, the buildup of pressure to the rear brakes is 0.5 times the buildup of pressure to the front brakes. It's not too bad, actually. But if this were for a race car, which doesn't have any ABS, we would want that crossover point to end up being a little higher than this. We could bring the proportioning ratio down a bit to keep more of the actual curve underneath the ideal curve. Here's one from the Summit Racing catalog. It has an adjustable actuation pressure through this knob, but a fixed proportioning ratio. It says 57% reduction, which means it allows only 43% of the pressure to get through. Let's change the ratio of our proportioning valve from 0.5 to 0.43, like the one in the Summit catalog, and see what happens. Now we have an actual curve that stays under the ideal curve until we are braking at just under 0.9 Gs. And the difference between the curves is not very big at any point. Not a bad result, really, but probably not good enough for a race car. We can tweak it one more time by reducing the activation pressure down to 3.3 newtons per square millimeter, and now we have something we can work with. You can see how that increased the difference between the two curves, but it did push our crossover point up above 0.9 Gs. We could leave it like that and call it a day, but we can also use our model to calculate if we're going to meet regulations. Most of the requirements in FMVSS 135 and ECE R13H deal with non-performance related things. Things like what the brake warning light needs to look like and under what condition it should light. They also talk about things like what the cap on the brake reservoir needs to say and how visible it must be. But there are also actual performance requirements, and we can calculate some of these from the data that we have. For instance, FMVSS 135 contains a failed boost requirement. In other words, there are requirements for how well your car must be able to stop in the case that your booster fails and you get no boost. It says that with a pedal pressure of no more than 500 newtons, which is about 112 pounds, the car must be able to stop in less than 168 meters, or 551 feet. And for the model we just built, it would be 84.9 meters, so we are well within the requirements. There is another requirement that we could calculate as well, but we need a bit more data than we have at this point, and that is the hill hold requirement. FMVSS 135 states that a vehicle loaded up to its maximum weight, or GVW, must be able to be parked on a hill of a 20% grade and with a force of no more than 400 newtons for a hand-activated parking brake or 500 newtons for a foot-activated parking brake. The parking brake must be able to hold this vehicle on that grade facing both up and down the hill. We have most of the data that we would need to calculate this requirement, but we would also need to have some information about the parking brake lever, and we don't have that yet. Later on, as the design of our car progresses and we design a parking brake mechanism, we can use our model to calculate the hill hold requirement too. One last comment that I want to make about regulation is that both FMVSS 135 and ECE R13H require that the vehicle be able to stop in the case that there is a single failure in the hydraulic system. In other words, if there is a leak in the hydraulic system and the hydraulic fluid leaks out, the car must still be able to stop by pressing on the main brake control, which is the brake pedal. This is why all cars for the last couple decades have had dual circuit hydraulic systems. There are two independent hydraulic circuits in the car, so that if one of these systems springs a leak, the other system will still be complete and be able to stop the car. Usually nowadays, each circuit attaches to one of the front wheels and one of the rear wheels. One circuit would service the front left wheel and the right rear wheel, and the other would service the right front wheel and the left rear wheel. That way, you would always have at least one front wheel and one rear wheel braking, even if there is a hydraulic failure in one of these circuits. We've talked here about the basics of the brake system design. What we've talked about will allow you to size the master cylinder, the calipers, and the rotors, but what we haven't talked about is any of the thermal performance. How fade resistant will the system be? Will the system be able to stop a car from 200 miles an hour, for instance? Those things we have not covered. We would need to get a much more sophisticated model that looks at things like the thermal capacity of the rotors, the pad area, the rotor cooling fins, the airflow around the rotors and the wheelhouse, and a number of other parameters. Here, though, you've got the basics of how to size a brake system and what brake engineers take into account when they design a brake system for a car. If you've enjoyed this video, please hit that subscribe button and don't forget to hit notifications, and we'll see you next time for more Suspensions Explained.